Hello everyone. My name is Nicholas Birkhimer. I'm a graduate student here at North Dakota State University in the Department of Soil Science. And today I'm going to be talking about my master's research, which was on the effects of cropping sequence, tillage, and manure application on pipeline reclamation in Western North Dakota. Now, before we really get into the research, I want to talk a little bit about the reasoning for this research, what happens on reclaimed pipeline right-of-ways, and also why this is an important piece of research for North Dakota in general. And the big reason for that is because there's going to be a lot of oil and natural gas extraction over the next 2 decades or so. By the year 2040, the United States is expected to increase the production of oil and natural gas by about 20%. Now, this is going to mean we're going to need more well pads to extract this resource and more pipelines to move this around. With these construction projects, we're going to need to disturb a lot of land in order to get these well pads and pipelines installed. What that's going to mean is that we're going to see about 230 to 260,000 square miles of land in the U.S. impacted within this 20-year time frame. And that's an area about the size of Texas, so pretty significant. Now, it's not going to be uniform across the country. It's going to be really centralized just in the pockets and areas where oil and natural gas production is occurring. That's mostly going to be in the states of Alaska, Texas, and North Dakota. To give you a better idea of what this looks like, here's a map of the state of North Dakota where we look at the density of oil and natural gas well pads within a 20-mile area. Those little hexagons are areas of about 20 square miles. And the darker the hexagon color, the more well pads you have within that 20 square mile area. You can see that the greatest density we have is over 61 hectare well pads in a 20 square mile area, which is a pretty significant disturbance. And as you can see, it's mostly concentrated within the Bakken and Three Forks region in Western North Dakota, around the areas of Williston and Watford City. There's also some production as well in the Williston Basin outside of that. So you can see just kind of the extent of what this could look like in the state of Vermont. From here, let's talk about what's going to happen on this land when well pads and pipelines are installed. So to give you an idea, here is a modeled undisturbed soil profile. You can see that we have a shallow organic matter rich A horizon overlying B and C horizons that are enriched in clays, salts, and carbonates. Now, what happens during a reclamation project is the right-of-way, which is going to be about 200 odd meters wide for a pipeline and going to be about 1 hectare size for a well pad. Topsoil is scraped from there and then placed adjacent to the right-of-way during the construction project. Subsoil is then excavated to a depth where the well pad can be plugged or the pipeline can be installed. Subsoil is then repacked over the pipeline or over the area where the wellhead was, and then topsoil is respread. So one of the common disturbances that we see happening here is that topsoil and subsoil can get mixed either by improper depth of scraping of topsoil or just general mishandling during the reclamation process. So then what you get is a soil profile that looks a little bit more like this. You have an organic matter diluted topsoil, so all that organic material has been kind of mixed throughout the soil profile, but also those carbonates, clays, and salts that were in the subsoil have been incorporated throughout the soil profile. And all of this can lead to pipeline right-of-ways that look a little more like this with really low areas of productivity. Now, on top of the soil mixing changing a lot of soil chemical properties, you're also going to see changes in soil physical properties, namely in the form of soil compaction. Now, you can think about having this heavy construction machinery needed to clear the right-of-way, install the pipelines, all that kind of stuff. You're going to end up with a soil compacted layer at the surface of where the subsoil was excavated, the topsoil was excavated, the exposed subsoil there is where all the machinery traffic's going to go over. Now, there's so much weight on there that it's going to lead to a failure of soil structure, compacting the layer in general, destroying soil pores and increasing soil bulk density, leading to a general loss in soil structure and a layer that's really hard for roots to penetrate. You can see that in this picture taken from our field study, where this undisturbed safflower root, safflower, by the way, which being a plant which has a well-known strong taproot that's able to break through soil compaction. It does well on the undisturbed sites, but then on the roadway and pipeline sites on the right-of-way, it has a much more difficult time being able to permeate the soil profile. So with that, let's look at our pipeline reclamation goals now that we better understand what these projects do to soil. Now, first thing we want to do is determine impacts of reclamation activity on soil properties. Soil is such an azeotropic system. It's very challenging for us to be able to understand exactly what you're going to get on each pipeline right away. For example, I mentioned in some cases, if you do have like a BT horizon with accumulated clays in the subsoil, and that gets mixed into the topsoil, you're going to see increased clay content. which can lead to increased water holding capacity within the topsoil, as well as increased cation exchange capacity, which is good for productivity, but that's not always the case. So being able to understand what actually happened on your right-of-way is very important. You also want to be able to restore your crop productivity to pre-disturbance levels. Like I said, that soil mixing, reducing organic matter, increasing pH, increasing salt levels, that's all going to affect productivity as well as that compaction. So being able to amend those and get those to a better place is going to be great. And a lot of that kind of goes into with our last point, which is addressing soil productivity changes that create an environment non-conducive to plant growth. Like I said, it might be beneficial ultimately to have a little more clay in your topsoil if that's possible, or if you do see some changes that aren't necessarily going to have a big impact on your plant productivity, that's not something to care about as much. But if you have really high pH or really high salt, that's something that you need to get at. So with these reclamation goals in mind, let's dive into the research project that we had, which kind of consists of two main parts. The first one, the first chapter of my thesis, looks at the effects of oil and natural gas reclamation on topsoil properties and analyzing that through meta-analysis. Now, the reason we did this is because we want to be able to better understand what potential changes to soil properties we might find on reclaimed pipeline right-of-ways. So first off, we searched the pool of existing literature on oil and natural gas reclamation and construction and looked at that to compile a resource of published data. We then used that to be able to look at an actual meta-analysis where we take our data, we analyze it to look at broad-reaching trends and determine consistent effects of oil and natural gas reclamation on topsoil properties, as well as if there is a consistent effect level. So if we can say, oh, we generally see an increase of bulk density of 20% between undisturbed and disturbed sites, that's going to be fantastic for informing stakeholders about some things that they can expect to happen on their right-of-way. But also to be able to inform stakeholders, we wanted to glean some best management practices from the published literature to be able to give people management options on the reclaimed pipeline right-of-ways. So to get a little bit further, we also wanted to be able to apply this by looking at a field study where we looked at the effects of cropping sequence, tillage, and manure application on pipeline reclamation in Western North Dakota. We had the opportunity to go study a reclaimed pipeline right-of-way that was installed in Williston, North Dakota in the spring of 2015. And we were able to, first off, see what the effects were on soil properties of this reclamation project. We were also able to go in and look at the effectiveness of 5 different cropping sequences to restore lost yields that we found over a 6-year time frame. So we're looking over the short term and the long term and see what we can get back to. And then finally, we also wanted to look at if there are other management practices that we could look at. So for example, applying deep tillage to be able to break up that compacted layer that we talked about, and also being able to apply surface manure to be able to restore those lost soil nutrients, namely in the losses that we saw to soil organic matter on the right-of-way, again, in order to restore crop yields. So first, let's get into our first chapter, which was the effects of oil and natural gas reclamation on topsoil properties, a meta-analysis. So first off, let's talk about our methods. How do we find these papers that we're getting this data from? So we started by searching the Web of Science database in the spring of 2021 using a search term represented by this figure here. What this figure basically says is our search term that we used said that we only wanted to see papers whose title, topic sentence, and abstract included the term soil and any combination of the words pipeline, well pad, or well site, and any combination of the words reclamation, restoration, installation, or right-of-way. This ended up in returning about 200 papers from the Web of Science search. From there, we looked through papers and we checked to see if each paper reported a soil property that was both reported on and off a right-of-way. We also looked at papers that were able to report data from before or after a reclamation project that was deemed to be a pretty similar thing. We also looked at just topsoil. So that was either just the top 6 inches or just in the uppermost soil layer. So we're just focusing on the topsoil properties. Now, this resulted in us getting about 27 papers being incorporated into this study overall. Let's give you a better idea about the data that we collected here. So this is looking at a summary of the papers included in the meta-analysis. The soil properties are reported in the order in which we talk about them in this presentation. We also report the units that these are all reported in, as well as the number of papers they were reported in and the number of observations. You'll see there's some discrepancy between number of observations and number of papers. This is because in some papers, we got to see more on and off right-of-way values being reported, whether that be over a series of time, if there were multiple right-of-ways, anything along those lines. Also, something important to note here, for some papers, we did get multiple values in terms of on and off right of way, but they didn't give us some measure of dispersion, so we were able to combine those values to get some measure of dispersion. How this matters is that it comes into our data analysis. So we use a random effects meta-analysis using the generic inverse variance method to be able to weight each study, and we use this to be able to analyze our on and off right of way soil properties. Now, we used, now data points were analyzed as expected value of percent change. What this means is that since we had such a variation of studies in terms of not only where they were conducted, but also in the magnitude in which they changed, we didn't want reporting raw values to throw off our analysis. So we reported percent change, kind of like I said earlier, looking for like a percent increase or decrease in bulk density organic matter, something like that. And then we also used an Egger test to be able to look for significant biases. And what this means is that you can get biases in your data through publication bias, through only wanting to report significant properties in some papers, stuff like that. And this ultimately resulted us in excluding total nitrogen from our meta-analysis, as it did come up as having significant bias. So with that out of the way, we had a couple soil properties that did result in significant differences that we want to talk about right now. So first off, we're going to talk about bulk density. Through meta-analysis, we found a significant increase of 23% in bulk density between undisturbed and disturbed sites. Now, normally this comes from heavy machinery traffic, like we talked about, going over the pipeline right of way. So that's going to lead to destruction of soil pores and increased compaction within that upper layer of the soil profile. Now, this also leads to a lot of other related soil variables being affected. So one, we see an increase in penetration resistance going with that, since it's going to be much harder for a plant root to break through a compacted soil layer. And also with that reduction in pore space, we're going to see a decrease in moisture content. The soil profile is able to hold less water and decreased aeration. So we're able to less easily move air and less of a space for soil microbes to be able to transfer through the soil profile. We also saw a mean increase in pH of 12% between the undisturbed and the disturbed sites. This kind of goes in that soil mixing that I talked about earlier. This usually results from alkaline subsoil materials and the carbonates being mixed with the topsoil during soil stripping and replacement on the pipeline right of way. Now, this mostly is going to be significant whenever you have a high pH soil to start with, or if you have a subsoil that's really loaded with carbonates, and that's going to really get you above a pH, let's say, of about 8, where you start to see significant decreases in soil nutrient levels. One of those examples being phosphorus. A study that we found soon et al. Found decreased phosphorus within corn stalks following reclamation, and then short-term following the reclamation project. And that was associated with high pH levels in the topsoil and those that phosphorus sorbing to the soil. So with that in mind, that's something to consider on some of your pipeline right-of-way projects. We also found a mean decrease of 10% in soil organic matter between the undisturbed and disturbed sites. A lot of this does come in, like I said earlier, with the soil mixing your topsoil with the subsoil is really going to dilute that. You're going to lose organic matter that way. But there's also a lot of soil mineralization that can occur, especially after you get that topsoil stripping. So what happens is that when you strip the topsoil from the right of way and store it in a stockpile, you're going to destroy a lot of the soil aggregates, and that's going to lead to a release in physically protected soil organic matter. Now, it's going to be somewhat protected when it's in the stockpile, but when you respread it, a lot of that's going to become plant available or available to microbes. So it's going to become easily mineralized or uptaken by the plants, and you can actually find some situations where you see significantly increased crop production on the right of way in the short term following your reclamation project, because all these physically protected nutrients are available and can just be eaten up immediately. But then you lose that stable organic matter source over time, which can lead to issues related to productivity. So that's something those are two avenues where we can really lose soil organic matter on pipeline right-of-ways, which is something that we see very commonly on these projects. We also saw a mean increase of electrical conductivity of 634%. This is pretty large, but note that it's mostly these, note that in this tree graph you see here, it's these bottom 6 observations from Soon et al., where you really see a lot of these big increases coming out. That's because a lot of this is tied with incorporation of subsoil salts with the topsoil. This means that in areas and regions where you have a lot of subsoil salts, whether that be through presence of the parent material or through leaching over time, you're going to see a greater potential for those to be incorporated into the topsoil during a reclamation project. So it's very important with this, soil EC, to be cognizant of or to understand your soil profile before going into a reclamation project, especially in regions where you know that subsoil salts or salinity can be an issue with productivity. And our last significant property that we found was soil calcium. We found a mean increase of 296% soil calcium between the undisturbed and disturbed sites. Again, very similar to EC, you find that a couple of these studies are really dragging this up. For example, the Coiffe-Gomboltenol studies, which were conducted in the Le Croix region of southeast France. Now, these soils where these studies were conducted were formed over a concrete calcareous matrix in the subsoil. This is basically just a solid wall in the soil profile with just calcium carbonate. So whenever that is accessed during the pipeline installation reclamation process, it's very easy to mix that in with the topsoil and then get significant amounts of increases in calcium carbonate. You can see here that we see increases between 2,000 and 10,000%. And again, it's also very important to note, I keep bringing up calcium carbonate, oftentimes in pipeline right-of-ways, calcium increases are due to calcium carbonate, which is incorporated in the topsoil, that dissolving and leaving free calcium ions within the topsoil. So this again is something to just consider as you go to a reclamation project. Now, the rest of our soil properties that we found within the meta-analysis within our search didn't produce significant changes. So for example, we didn't find significant changes in soil texture, total nitrogen, cation exchange capacity, phosphorus, or magnesium. Now, this doesn't mean that these aren't things to keep an eye out for. For example, we talked a little bit about some studies have found increases in clay content. For example, one study found that an increase in clay content was also associated with an increase in cation exchange capacity in the topsoil on a pipeline right-of-way. Talked a bit about changes in phosphorus as well. And, some studies have also looked at the changes in water content that come from changes in soil texture, mostly resulting in changes in clay and sand content. So while this meta-analysis didn't find any broad-reaching changes in these soil properties, that doesn't mean that these aren't things that ought to be considered or observed on your reclaimed pipeline right-of-ways whenever you're looking at a reclamation setting. So now let's look into some management practices that we found through this meta-analysis and some things that stakeholders can do potentially on their right-of-ways to be able to limit some of the impacts of these construction projects. So first off, reclamation done when soil water content is low can limit increases in bulk density. Now, what Nielsen found was that pipeline right-of-ways that were installed and reclaimed in fall compared to spring had a lesser increase in bulk density. This is because in the fall, soil conditions were much drier than the spring, and so that led to a much higher soil strength in the fall, so it was less susceptible to compaction on the right-of-way. So that can be a really important thing if compaction you'll find can be a big issue on your right-of-way. Also, another thing is that we talked about increases in carbonate and salt content on your right-of-ways. It has been found that these can be generally leached over time. Nath found, especially in 2014, on her study site, that significant precipitation events led to significant decreases in topsoil pH and EC because those incorporated salts and carbonates were being able to put into solution and then leach down to the subsoil. Now, this is very challenging in semi-arid regions where in general soil water is going to be moving up the soil profile, but there are some situations where this can be a natural way to reclaim your soil and ameliorate these properties. And last but not least, being able to restore your soil nutrient levels, namely in the forms of carbon and nitrogen. Some studies have found that in the short term, you can incorporate something like manure, which is going to be able to decompose much more readily and build that soil organic matter and give you an immediate boost in getting your productivity up. And in some cases, more of a long-term source, like a straw that's going to decompose more slowly and provide you steady sources of CNN over time, while also giving you some soil protection and long-term trying to rebuild those microbial and soil organic matter levels in your soil. So what we learned from our meta-analysis was one, that reclamation can often lead to increases in soil bulk density, pH, EC, and calcium content, and also decreased soil organic matter levels. And we also found some management practices that you can use to limit the impacts of reclamation on soil properties, namely by performing reclamation activities during a time while soil moisture is low. Also being cognizant of soil mixing, being able to potentially plan for applying moisture in some way, whether atmospheric or another way, to leach those carbonates and salts into the subsoil, and then incorporating organic material to be able to return your soil organic matter levels to a level where you're going to have a lot more productivity. So with these in mind, we can now move into our field study, where we look at the effects of cropping sequence, tillage, and manure application on pipeline reclamation in Western North Dakota. So for our study site was conducted at the Williston Research and Extension Center, and it began in the spring of 2015 when a 3-foot diameter water pipeline was installed at the Williston Research Extension Center. This construction project resulted in about 36 acres of agricultural land, which was previously managed as a long-term no-till system, being disturbed. Now, we ended up with 3 distinct disturbance sites here. You can see here we have the roadway where all of the construction equipment went and all of our large machinery. We had the pipeline trench where the pipeline was actually laid, and then adjacent spots on the farm, which were kind of undisturbed and, like I said, still managed as a long-term no-till system. Now, for our cropping sequences, we had 5 cropping sequences. Between 2015 and 2018, we managed these as 5 unique cropping sequences. First off, we had our control treatment, which was continuous wheat. This was to try and mimic or show what would happen if someone went with a no action management plan. They're just going to continue going with wheat in this, and that's kind of our base level of what could happen. And then treatments 2 and 3, we looked at different variations of implementing wheat, peas, barley, and safflower. We chose peas because they're, 1, very sensitive to compaction, and that would really pop up rather quickly within our results. And 2, we chose safflower because, like I mentioned a bit earlier, it has a very strong taproot and is able to break through soil compacted layers and access deep soil moisture, and can be really resistant to some kinds of change like this. And treatments 4 and 5, we looked at different orders in planting a cover crop mix and a wheat cropping sequence. The reason why we chose cover crops is because cover crops have potential to be able to improve the productivity of the subsequent crop, namely by potentially conserving soil water, and also by being able to support soil organic matter development, while also being able to prevent soil erosion through being able to provide the soil with some cover. You can see the cover crop mix that we have below with CC mix. Now, in 2019 and 2020, what we did was we looked at response testing. So we planted everything in wheat in 2019 and everything in safflower in 2020. And this was to kind of get an idea of what different effects were between our different cropping sequences. Now, these started in 2015. In 2017, what we did is that we went in and we applied some sub-treatments. So one is that we looked at applying deep tillage to a depth of 18 inches to break up that soil compaction. And then we also looked at applying cattle manure to plots prior to tillage. We applied manure at a rate to provide 700 pounds per acre of carbon and 200 pounds per acre of plant available nitrogen. Like I said, to be able to try and kickstart getting those soil nutrients and soil organic matter levels back to an area where we want them. So with all this going on, we'll give you a better idea of what our study design looked like. So first, we had our 3 different disturbances. We had our control site, which was adjacent to our roadway and pipeline, which were very close together. All of our disturbances were about 1,260 feet long. This was to accommodate for having plots for all 5 of our cropping sequences, with 4 replicates of each going down north to south from the disturbances. And then each of these plots were 15 feet wide. Now, next, let's talk about our sub-treatments. So what we did originally is that we had 45-foot by 15-foot plots. That's our main cropping sequences. And then in 2017, when we applied our sub-treatments, we subdivided those into 3 plots, one of which was continually managed as no-till, one was applied deep ripping, and one was giving manure application with deep ripping coming after that. So that's our study design. Let's talk about collecting our actual data that we used in the study. So first off, crop yields were collected annually and analyzed in bushels per acre to give us an idea of what our yields were. That was for all of our grain crops. For our cover crop mix, what we did is we took a 1 meter by 1 meter quadrat, and we took above ground biomass and dried that. We took that as a surrogate for above ground productivity on the cover crop plots when that was implemented. We also took soil data in the fall of 2020 to be able to look at long-term what the effects of the pipeline reclamation project were on soil properties. So we looked at soil organic matter, inorganic carbon, pH, electrical conductivity, and the microbial community composition. We also looked at soil texture. We collected that data in the fall of 2017, and we're also going to get into some penetration resistance stuff. We collected that in 2016 and 2019, and the graphs that we present will tell you which year each data set was collected from. Now moving on to our data analysis. So instead of just looking broadly across all of our crops in terms of bushels per acre or kilograms per hectare, we wanted to be able to get a more relative idea of what was happening. So to analyze our crop yields, we looked at relative yields. That be, we took the yields for plots on the roadway, compared it to the adjacent plot in the undisturbed, and we did the same for the pipeline to get relative yields for each treatment and sub-treatment in between disturbances. For our soils data, everything was collected from the 0 to 6 inch depth and was analyzed between disturbances. So we didn't feel like we needed relative yields for this. It would be much more appropriate to just analyze things as their raw units, for example, soil organic matter as a percent soil organic matter content. Now for our data analysis, we went with non-parametric statistics, and we used a Kruskal-Wallis test to be able to test significant differences between treatments at different levels. So we used a significance level of P is less than 0.05. If we did end up finding significance, we used Mann-Whitney-Hughes test to be able to use mean separation to see which treatments were significantly different. So from here, let's start with our soil property discussion, and let's look at our effects of reclamation on soil properties. So what you're looking at is you're looking at each column. You'll see each of our different soil properties we looked at, that being organic matter content, inorganic carbon, pH, electrical conductivity, and then clay, silt, and sand for our texture analysis. Now, reading down, you'll see our disturbances, undisturbed roadway and pipeline. And for each value you see within a column that does not share the same capital letter, that means that they're significantly different from each other as per our analysis. So you'll see for organic matter, we have significantly lower organic matter on the pipeline compared to either the roadway or the undisturbed. One thing that this could mean is that we saw a lot more soil mixing on the pipeline compared to the roadway. I mentioned earlier that one of our big avenues for soil organic matter losses are through mineralization across the right-of-way, and this is much more of an even process across the right-of-way. So with that kind of being kind of set across the entirety of the right-of-way, it stands to reason that increased soil mixing would lead to further reduced organic matter levels on the pipeline. Now, this also kind of pops up within our next three properties, inorganic carbon, pH, and EC. You can see for all of these, the lowest level is on the undisturbed. The roadway saw significantly higher levels of inorganic carbon, pH, and EC than the undisturbed, and the pipeline saw the highest level of these of all. For inorganic carbon, again, a lot of this comes from carbonates in the subsoil being incorporated into the topsoil through soil mixing. This can lead to an increases in soil pH like we see. What I think is very interesting is that the roadway, you see that we get a median pH of about 8.0. That's about where you start to see a lot of decreases in soil nutrient availability, which can be a big challenge. Now, this is significantly less than the pipeline pH levels at 8.13. Now, with there being such a little jump, but still a significant increase, what this tells me is that we're seeing a consistently slightly higher pH on the pipeline than the roadway. While this might not necessarily be a big deal in terms of productivity, since we're kind of reaching that threshold where things get a little tricky in terms of like actual crop production, it still is an interesting thing to look at. And finally, for EC, again, same disturbance pattern. The important thing to note here is that our highest EC value we see here is 0.36 decisiemens per meter, which is well below the level of 2 decisiemens per meter at which most crops experience salt stress that'll be able to reduce crop productivity levels. So with that in mind, this is representative of soil mixing happening, but it's not necessarily a big deal for us in this situation. Now, we also do see some slight changes in soil texture. It's important to note that these changes in soil texture did not result in a change in the soil texture classification by the NRCS for these soils, but it just shows a slight shift. Now, while there might be some slight change in cation exchange capacity and water content as a result of decreased clay content between the undisturbed and the pipeline, and maybe some greater ability to move water or less compactability with the change in sand content, this is not necessarily something that's a big deal for us to worry about on this right-of-way itself. What is interesting is when we look at our penetration resistance and see what differences we got there. So this is penetration resistance data that was collected in the fall of 2016 from a depth of 0 to 30 centimeters, which is about 1 foot. What you look here is I just look across the x-axis. That is our penetration resistance level as we go down the soil profile. What's interesting is that the dotted line you see there, that is the level which is about 2068 kilopascals, at which plant growth essentially stops as the soil is too compacted for plant roots to be able to penetrate that. We do not break that for the roadway, sorry, for the undisturbed or the pipeline, but the roadway gets above that level between like 12 and 15 centimeters, which is really limiting topsoil availability for our crops on there. It means less access to water, less access to nutrients, all that kind of good stuff. What's very interesting also is that the pipeline and the undisturbed are largely similar, which kind of says that the topsoil could have been really well placed back over the pipeline with, maybe potentially a little bit more care, or there was less of a effect of machinery running over it as well, since it is so similar. Now, what's interesting, as well as we look at 2019, 3 years later, we're still seeing those issues with the roadway. But what I find is interesting is that we have a slight shift in the pipeline. You can see now there's a definite separation between the pipeline and the undisturbed in terms of penetration resistance. The pipeline is now just noticeably higher. Part of this is because we did have a subsidence occur in 2018 following multiple significant rain events. Now, you can think about whenever you place the soil back over the pipeline, there's a lot of pore space left in there because we didn't necessarily do a perfect job in terms of replacing the soil. So what can happen is that whenever significant rainfall events come through, it reduces that soil strength, and then the soil can kind of crush in on those porous spaces. What this ended up happening is, what it ended up leading to is a subsidence that was about 2 meters wide and for the most part about 18 inches deep at the deepest part, but up to a full 2+ feet in some areas. Now, as you can see with Tom standing there in the background as our researchers went out to look at this, it's really difficult for a combine to be able to get in there and harvest whatever crop you had. So while you're also getting, again, problems with compaction here, you're also going to find it much more difficult to get in and harvest whatever crops you might have. So something, again, to consider on pipeline right-of-ways, issues that you might be coming into. Now, the last thing we're going to look at in terms of soil properties is our effects on the microbial community. So again, you're looking across, now when you're looking at the top, you're looking at differences between disturbances, our undisturbed roadway and pipeline, and then going down, you'll see our differences between the microbial abundance, and then differences between our vascular mycorrhizal fungi, gram-negative and gram-positive bacteria, and the ratio of gram-positive to gram-negative bacteria within the soil system. So first off, you can see the undisturbed had significantly greater total microbial abundance than the roadway or the pipeline. So again, whenever you're looking at letters here, if a median within a row does not share the same letter as the other medians of the same row, you're going to see a significant difference in soil properties. So we saw our highest microbial abundance on the undisturbed, and then significantly lower on the roadway and lowest on the pipeline. A lot of this is due to soil disturbances that we saw, again, destruction of aggregates, increasing soil pH, creating a less hospitable soil environment, and also losses in soil organic material leading to that. What's interesting is that we do see the opposite trend from total microbial abundance in terms of our vascular mycorrhizal fungi. You see that we saw the greatest relative abundance on the pipeline compared to the roadway or the undisturbed. Now, relative abundance is a measure of how much of the total community is composed of by this one type of microbe. So what we find here is that there's a significantly greater part of our smaller community is made up of AMF on the pipeline than the roadway or the undisturbed. When you look at this in terms of total abundance, the total amount of AMF is the same across all disturbances. Now, what this could mean is that AMF is relatively robust in terms of being able to resist disturbance. It could also mean that it's able to establish itself more quickly. We're not 100% sure, but this is a really interesting finding from the study. We also saw a shift in the gram-positive and gram-negative bacteria. Why this is important is that gram-positive bacteria tend to get more of their carbon sources from a more slow-releasing, slow-producing source in the soil. So think about your slow-releasing, physically protected soil organic matter, whereas gram-negative bacteria actually get a lot of their carbon biomass from quick-releasing sources. So that is your detritus, decomposing crop residue, or decomposing soil microbes. So while we see this shift, in the ratio of gram-positive to gram-negative bacteria went from 1.3 on the undisturbed to 1.13 on the roadway to 1.04 on the pipeline, you can see kind of that effect of losing that long-term soil organic matter sources that were physically protected by seeing that decrease in gram-plus bacteria and more gram-negative bacteria having to rely on those quick-releasing sources across our disturbances. So to kind of give a summary of our soil takeaways here, we saw decreases in soil organic matter and increase in soil pH to levels where crop productivity is likely going to be affected on the pipeline and roadway disturbances. We also saw significant increases in penetration resistance on the roadway compared to other disturbances, with a slight increase on the pipeline that's likely potentially due to the subsidence that we saw. And we also saw a shift in the soil microbial community, mainly that shift and mainly decrease in the gram-positive to gram-negative ratio, showing changes in soil carbon cycling on the pipeline. Now from here, let's move into the actual meat and potatoes, what's happening to our crop productivity. And it's very important, like I said earlier, to be able to understand what's happening in terms of what we lost initially. So in the first year following reclamation, you can see we saw significant yield losses between the undisturbed, the roadway, and the pipeline. Our greatest losses were in peas. Like I said, they're very disturbance sensitive, and we saw yield losses between 74 and 84%, which can be devastating for some producers. Our most robust treatment ended up being wheat on the pipeline, but then wheat on the roadway and our cover crop mixes ended up being rather similar. So we saw across the board, we're seeing significant yield reductions, which can be quite problematic for a lot of producers. So let's see kind of over time what happens and how our treatments and other effect levels were able to help us with along the reclamation process as we move along from this initial disturbance. So first off, we're going to look at our main effect levels that resulted in significant differences. So when we talk about main effect levels, we looked at years since the reclamation happened as one effect. We looked at cropping sequence, we looked at disturbance, and we looked at subtreatment. So for year effect, you can see again kind of this idea of earlier years being the lowest producing, latter years being the highest producing. So again, for the year table, you're reading down. So whatever in that median column, whatever medians do not share the same capital letter are significantly different, with our lowest year overall being the first year producing about 40% on the disturbed sides compared to the undisturbed. We then jump up to 78%, so we almost double our relative yields in 1 year. And I think it's very important to note that between 2016, 2019, and 2020, all of those relative yields are not significantly different from each other, actually ranging between 78 and 81%. Now you may be wondering, why are the yields so much higher in 2017 and 2018? Well, we had some interesting weather conditions in both of those years. In 2017, there was a significant drought that affected the region, which really reduced crop productivity. So while relative yield was higher, total yield across all of our sites was much, much lower due to drought. So basically what happened was the drought negated the effects of the right-of-way such that nothing was producing good. So that happened that year. And the opposite kind of occurred in 2018. What happened there is that we had much more rainfall. Like I said, that's when our subsidence occurred, but also that is when we got the most rainfall throughout the study. So that effect of having so much soil moisture was able to kind of limit those effects. In fact, whenever we looked at our cropping, our relative yields between our cropping sequences just in 2018, they were all not significantly different from each other because we had those rain events. So considering these things, again, water is the great equalizer, as has been said. So that's kind of what's happening within those years. Otherwise, we hit a long-term reclamation value within the first year following our reclamation project's completion. We also saw some significant changes between cropping sequences. What I think is important to look at, that C1 treatment, which was our continuous wheat sequence, that is on par with our long-term reclamation idea that we're kind of getting. Between 78 to 80%. We hit that overall over the course of the study. So that no action wheat treatment ended up getting us to that level. We did not see a significant difference between wheat or either of our cover crop sequences, which were treatments 4 and 5. They were a slightly higher, but not significantly higher. So considering that those didn't necessarily lead to increased profitability over that time, as we weren't able to commodify those cover crop years, this is something to consider for producers, that this might not be a route you want to take. One thing that we did find also is that first year pea planting over time did lead to significant did lead to the highest yields out of any sequence, with about 90% overall. Now, part of this was you did see we did have really low yields the first year, but after that, they shot right up. Some reasons for this might be that the peas that we planted in that first year, peas are able to fix atmospheric nitrogen and can thus, improve the soil nutrient levels. And also with such poor yields the first year, you're able to conserve a lot of water for subsequent years. So that is definitely some ways potentially that we did see increased yields over time from that. Also, you can see treatment 2 had the worst by far, and that was our second year pea planting treatment. Now, what's interesting for this is like, why don't we get that same effect from the other pea planting treatment? Now, part of it might just be poor timing. In 2016, when we planted the peas, going into 2017, we had that big drought. So whatever nitrogen that we might have gotten from those peas wasn't as available to plants the next year due to drought conditions. And then furthermore, it's important to note that in 2018, when we had that subsidence, the plots that were affected the most just happened to be plots that were planted in that treatment too. Now, we weren't able to harvest those that year, and that would probably lead to some change over time. But it's important to note that plots on the roadway that were also planted in treatment 2 saw this same effect of really reduced yields and not doing that well over time. So there are some things to consider about, something might have happened here in terms of this sequence not producing as high yields as first year pea planting. So moving on to effects that didn't have a significant results, we did not find a significant effect of the tillage subtreatment on relative yields. One of that being, deep tillage and then deep tillage with manure application. We also didn't see significant differences between disturbance levels. What's interesting with the disturbance levels, this kind of says to us, you can largely, over the course of the whole reclamation project, you can largely manage your roadway and your pipeline similarly, and you're not going to have necessarily huge differences in yields. And this can be really helpful for a lot of producers and stakeholders for reducing the amount of granularity that you need in order to properly look at your pipeline right of way. Now, for the sub-tillage treatment stuff, one of the big things that we think is going on here is that, yes, while compaction is compaction is not important, deep tillage to break up compaction can be very important. The problem that we're seeing here, though, is that we've broken up the compaction. We haven't rebuilt that soil structure that we've talked about is often lost during these construction projects. So being able to apply organic material within the soil to actually re-aggregate, we could ultimately see some ameliorations in soil properties. Laskew found in their 2012 study that whenever they injected pelletized organic matter into subsoil on reclaimed pipeline right-of-ways, they were not only able to see increased nutrient content, but they also saw reduced bulk density due to increased aggregation over time. So with that, maybe that's an area of further research where we can see greater reclamation effects over time, as opposed to just applying deep tillage or applying manure on the surface. Back to the manure thing really quick. It is interesting that the manure didn't lead to a significant increase in productivity. One thing to note is that studies have shown that whenever you apply manure on a pipeline right of way, or manure and fertilizer, which was done in the study as we were applying fertilizer every year, that didn't lead to a significant difference in crop yields. So with that in mind, applying the manure with the fertilizer might have been a little bit of an overkill in terms of we already were getting the nutrients that we needed. This wasn't needed at this point in the study since it was 2 years post-reclamation. So it's something to consider as well. Now, we want to give you a better idea of what we're looking at and visualize what's happening with our cropping sequences over time. So you can see that everything's starting off really low, and this is comparing the pipeline to the undisturbed. So that dashed line at the 1 level, that is our on level with the undisturbed, that is our reclaimed state. So you can see that we do jump up there in those 2017 to 2018 years, we're getting pretty high. Even 2016, we're getting better than 2015. But once we hit 2019, we're leveling off quite a bit. So once we hit this state, again, 5, 6+ years down the road, we're probably not going to see a lot of big changes in terms of reclamation. So that 80% mark or whatever you're going to be hitting is roughly about where you're going to be staying. And this really is, like I said earlier, this is the same story on the roadway. It's actually a little bit tighter on the roadway compared to the pipeline. You can see that we had big push up to 2017 when we had that drought year, but we have that really tight distribution in 2019 and 2020 where things have leveled out, and we're probably going to stick there for the long term. So the idea with this is that whatever you're going to be doing with your pipeline right of way in terms of reclamation, you want to hit that quick to be able to try and hit your reclamation goals, whatever those might be. So also now we want to kind of bring everything back. We've looked at what's happened with these treatments over time and kind of where we started. Let's look at where we ended up. So this is just our raw safflower yields between the undisturbed roadway and pipeline for our 5 cropping sequences in 2020. So again, you're going to be looking at the columns here, reading down, and whatever median is not followed by the same capital letter, they're significantly different between each other. So for our continuous wheat, we did see significantly lower safflower yields on the pipeline than the roadway and the undisturbed. It is nice seeing that homogeneous treatment between the roadway and the undisturbed, but the pipeline was still giving us a little bit of trouble. You can see that the only treatment in this year where we did see homogeneous yields across the entire right-of-way was with that first-year pea planting yield treatment, where we had homogeneous yields across all sites. Again, with the cover crop sequences, we see something very similar to the continuous wheat, where we aren't necessarily fully across the right-of-way getting homogeneous yields. But then what's interesting as well is that barley pea treatment, we're seeing significantly lower yields on the disturbed sites and the undisturbed site. Again, showing some kind of effect is going on there with that later pea planting than that earlier pea planting. Again, a lot of this can potentially be attributed to that drought year following our pea planting. So what are our conclusions then coming out of our cropping sequence stuff? So first off, our reclamation level was about 80% of the undisturbed in the long term. This is something that you can look at and think about when you're going into these reclamation projects. We found that continuous wheat did not produce significantly different yields from a cover crop wheat treatment. Therefore, that's something to consider whenever you're going into these projects. If you do want to manage things with cover crops to prevent erosion and maybe save some water and stuff like that, that's great, but that's not going to lead to significant increases in wheat yield following that over time. We also found that first year pea planting produced the greatest relative yields, potentially due to getting that nitrogen in the soil quickly, as well as being able to conserve soil water through low yields on the pipeline. And then also that tillage and manure applications didn't result in significant increases in relative yield, but being able to do more research in the future in regards to applying early organic amendments and being able to put organic material deeper in the soil profile to allow for further aggregation could be some really interesting areas for the research to lead to pipeline reclamation. So for acknowledgements, I'd like to thank the North Dakota Oil and Gas Research Program for providing funding for this project. I'd also like to thank the faculty and staff at the North Dakota State University School of Natural Resource Sciences for providing tutelage, expertise, as well as support for this project over the 6 years of the study, as well as the faculty and staff at the NDSU Research Extension Center in Williston for being able to put in so much hard work into this project, helping us get all the data prepped and helping with field work. If you have any questions, my email is printed on the screen, and thanks for listening in.